Hi, I'm Andrea. I'm a PhD student at the Max Planck Institute for Extraterrestrial Physics in Munich, and this talk is about how a smarter understanding of our cosmological parameter space can help us gain insight in the statistics of dark matter halos, and in particular about the halo mass function. I'm conducting this project in collaboration with my supervisor, Ariel Sanchez, and with Andrés Ruiz of the University of Córdoba in Argentina. I want to additionally thank Fabian Balzer, Sofia Contarini, and Christoph Zaulda for helping me with making this video. So the halo mass function is one of those key observables in large-scale structure that help us relate what we see, a distribution of tracers of the dark matter field, to the underlying cosmology, like you see in this slab from a cosmological simulation. To do this, we need, of course, reliable models to convert the tracer information into cosmological constraints. The halo mass function is one of these powerful tools. It can be used as a target observable itself, like one does, for example, in studies of cluster cosmology, or it can be used as an ingredient, and a key ingredient actually, to build models to describe statistics of other tracers of the large-scale structure. The concept behind the halo mass function is extremely simple. We take a catalog of halos, or of clusters if we're observing the real world, we weigh them, assign a mass to each of them, and then we count them. We make a histogram, a distribution, so to say, of how many halos per unit volume and per unit mass. And this is the halo mass function. We model it, as you can see from the equation on screen, with another distribution, the little f on the right-hand side, which is generally called the multiplicity function, and depends on this strange variable, the peak height, nu, which is just the inverse of the RMS variance of the linear overdensity field at the scale of the halos we're interested in. This variable is quite powerful at describing the statistics of halos, so much that if one takes just simple assumptions and tries to build an analytical model, like the spherical collapse or an excursion set of halos, one finds out that the halo mass function is entirely described by this quantity. It's a so-called universal mass function. We will come back to this topic of the universality or non-universality of the halo mass function in a few minutes, but first let me take a moment to describe the framework that the work is grounded in, the so-called evolution mapping. It is a way of splitting the cosmological parameter space in two different sets of parameters based on what they do, what effect they have on the linear matter power spectrum. So you have a linear matter power spectrum of a reference cosmology on the plot, in the plot on the left, and we can see that if we vary a parameter like AS, we rescale its amplitude. We just bring it up or down depending on how we vary it. While there are other parameters, such as the physical density parameters of cold dark matter and baryons, that do something more complicated. They change the shape of the curve that we see. This is the same for the spectral index NS. And so we can split the parameters in those that change the shape of the linear matter power spectrum, the so-called shape parameters, and the others, the ones that do just as AS. They just rescale the amplitude. We call these the evolution parameters. And we know that they all have the same effect. They're completely degenerate at the linear matter power spectrum level because they enter, well, the primordial power spectrum, thanks to AS, and only the growth factor, the linear growth factor, that does not depend on K, and so the only effect that it has is to rescale up or down our linear matter power spectrum. And the idea is that the effect of all of these parameters can be summarized in one number, so to greatly reduce the dimensionality of the cosmological parameter space. This number quantifies the amplitude of the linear power spectrum, and it's what in cosmology is generally done with sigma 8, except that sigma 8 in this context won't work, because the scale on which we filter the density field depends on h. It's 8 over h megaparsec. And h is a mixture of shape and evolution parameters, and so it obscures this perfect degeneracy and this splitting of the parameters into these two sets that we just operated. So we need to redefine our sigma, defining the filter on a fixed comoving scale in megaparsec without any cosmology dependence. Since 8 over h for a reasonable value of h is very close to 12, we define it to be 12 megaparsec, and this is how we come up with this new variable sigma 12 that just describes the overall amplitude of the power spectrum given the cosmology and the redshift which we evaluated at. This is all good at the linear level, but then what about the nonlinear, the actual density field and its power spectrum? And this was the reason to run the Aletheia simulation suite, which features 9 different cosmological simulations with 9 different, actually very different cosmologies with crazy values of some cosmological parameters, from a lambda CDM to a curved universe to an Einstein de Sitter universe, but all sharing the same set of shape parameters, so that once we evaluate them and at the same values of sigma 12, as we do with the snapshots of the simulations, by construction, the linear matter power spectra of these models are exactly the same. And we then measure the nonlinear matter power spectra from the simulations, and we see that the evolution mapping degeneracy nearly perfectly holds also at the nonlinear level, except for the small differences you see at small scales and at late times characterized by the higher values of sigma 12 that we use here as a time variable, basically. These differences in the matter power spectra are due to the different histories of structure formation that the different models follow, getting to the same value of sigma 12, due to the differences in the evolution parameters between them. And we found that these differences are very well described by this variable, x, which is a variable that enters the perturbation theory kernels and is very suitable for describing these small departures from the evolution mapping degeneracy. Incidentally, this is also true for the nonlinear velocity field, as it was shown recently in a paper by my fellow PhD student Matteo Esposito, and I encourage you everyone to check out his paper for the extension of evolution mapping to the velocity divergence power spectra. So we will measure the mass function in the Aletheia simulations and see how they look, but along with that, we want a sort of zoom in on the model 0, the reference lambda CDM cosmology that we have among these. And to do this, with that same cosmology, we ran another suite of simulations called the Aletheia mass. These all have the same reference, Planck 2018 lambda CDM cosmology, but they have a lot more particles inside them, and they come in different box sizes so that we can access a wider range of mass, and we can evaluate them at more values of sigma 12 to have a better coverage also in the time domain. In all of our simulations, we identify halos with the Rockstar halo finder, one of the most common halo finders used in the literature. And now we're finally ready to see some mass functions. Now, when we look at the mass function in the Aletheia mass simulations, what we can immediately see from the top panel of the plot here, where f of nu is plotted, is that universality doesn't really hold. F of nu is not really entirely described by the peak height, and this is by no means big news. It has been known for quite a long time that the mass function exhibits non-universality, and there have been many attempts at modeling such non-universality. Most of them are given in terms of fitting functions for f of nu, calibrated on numerical simulations, which is the same that we will try to do in this work. The most commonly used prescription is the one given by Tinker and collaborators in 2008, which has a scaling of the fitting parameters with redshift to model the non-universality. To this prescription, we refer our residuals that you can see in the bottom panel of the plot, and you can see that at high redshifts or low values of sigma 12, you can quite easily, even just in a lambda CDM cosmology, reach 10 or 20% shifts with respect to the theoretical prediction. Now, knowing about evolution mapping, can we model the non-universality in terms of how the history of structure formation goes in a given cosmology? And if we turn to the halo mass function in the Aletheia simulations, we see that there is a spread across the mass functions of different models that have different histories of structure formation. Especially if we look at the bottom right plot here, we can see that the spread across different models appears to be more or less in the same order as we saw it for the nonlinear matter power spectra we saw before. So maybe we do have a possibility of modeling this in terms of x. And actually, we can do something a little more refined, Since we need to account for the histories of structure formation, we can integrate X, convolve with a Gaussian kernel, as you can see here in the equation, whose standard deviation, which we name eta here, effectively counts as a memory parameter. It parameterizes how much the halo mass function remembers of the history of structure formation in any given cosmology. This is one of the parameters that we will use to model the halo mass function, along, of course, with the peak height nu. But there is an additional dependency that we need to take into account, which is the dependence on the shape of the linear matter power spectrum. This dependency was pointed out by recent works, especially by Andrea and collaborators in 2022, and it can be characterized with the tilt of the linear matter power spectrum and effective at a given scale corresponding, for example, to the Lagrangian radius of the halos. We find, though, that we can better fit the data from the simulations if we fix the evaluation of n effective at the typical scale of the collapse of halos at any given time, which is given by the value set by nu equals 1, the scale set by nu equals 1. You can see on the right a plot of how this function looks as a function of sigma 12. This is the same for all the simulations that we use for the fits because they have the same set of shape parameters. So with these three variables, the peak height nu, x integrated, and then effective at nu equals 1, we can try and build a better prescription for the halo mass function and see how it performs with respect to the existing prescriptions. I won't show you the actual functional form of the halo mass function of f of nu. We're still polishing the final details and it's not been published yet, so have a bit of patience for this. The first fits that I'm going to show you are all referred to halo catalogs and halos defined with an overdensity threshold of 200 times the background matter density. This is the same plot that I showed you before, just there is one line per snapshot here. I took a weighted average of the different boxes in the bins where they overlap to avoid crowding the plot too much. We calibrate a new recipe for f of nu, and this is how they look like now with respect to our prescription. So they shrink, the residuals shrink very, very much. If we zoom in, we can see that it's actually, we reach percent level accuracy on this lambda CDM suite of simulations, the Aletheia mass, that span a very wide range in redshifts from sigma 12 of 0.2, which corresponds roughly to a redshift of 4, to the last two snapshots. The last one is at sigma 12 equals 1, which in a lambda CDM cosmology would be in the future with respect to us. As well as a wide range of masses, which you can see if I rephrase the plot with mass on the x-axis. It's more than 4 orders of magnitude in mass. This is, however, all fitted and tested on lambda CDM. What about we try on different cosmologies? So we go to the Aletheia simulations that have a very wide range of evolution parameters, very different across them. And this is how they look now. So the dashed lines are the same residuals that we saw before with respect to the prescription of Tinker and collaborators, while the solid lines are the ones that we have now. So also with this very wide range of evolution parameters, very different formation histories, we can reach percent accuracy. This is, however, only simulations that the model has been fitted to. So what about we test the new prescription on something that it has not seen before? And here come the Aletheia EMU simulations. This is a suite that was originally built and run for a different purpose that features different cosmologies that vary evolution as well as shape parameters. So the linear matter power spectra here have a different shape with respect to the one that we have fitted our halo mass function on. And you can see from the plot that also here with these 10 subsampled cosmology, all evaluated at different values of sigma 12, we reach percent level accuracy with the top shift being at 2 or 3% at most. So also on cosmologies and on data that it has not seen before, the new prescription for the halo mass function performs very, very well. And now the final step is to try and extend the model to halo catalogs built with halos identified with different overdensity thresholds. And you can see in this final slide, with a lot of plots crowded with both the Aletheia mass and the Aletheia simulations together, that refitting the models over a wide range of overdensity thresholds yields residuals that are of at most 5% for the highest overdensity thresholds, which are the ones for which the mass function is more difficult to measure. And this leads me to my conclusions. So with evolution mapping, we were able to fit the halo mass function based on the different histories of structure formation that each cosmology follows. And this allows us to find a fit that fits the 200 background catalogs to a percent precision, percent accuracy, and the highest overdensity thresholds to an accuracy of at most 5%, but actually much less in most cases. And this concludes my talk. I hope you enjoyed, and if you have any questions, don't hesitate to ask.